Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available. Okay, welcome to this presentation. It's my great pleasure to welcome Professor Zhenghua Lin to give us the lecture on HMM-based speech synthesis. And Professor Lin currently teaches at China University of Science and Technology, and he has a very, very nice, strong group over there doing speech synthesis. And he recently arrived at University of Washington here to spend 1 year working on various aspects of speech and perhaps some multimedia. So I take the opportunity to invite him to introduce speech synthesis here. So hopefully we all can enjoy his talk. Okay, so I'll give the floor to Professor Lin.
Thank you. Thank you, Lee, and good morning, everyone. And hello, the listeners here and the listeners over the internet. It's really my great honor to be here and talk something about speech synthesis technology. And my name is Zhenghua Lin, and now I'm a visiting scholar at the University of Washington, and I come from USTC in China. Today, the topic of my presentation is HMM-based speech synthesis, its fundamental and some recent advances. This is the outline of my presentation. At first, I'll give some review of the state-of-the-art HMM-based speech synthesis techniques, including its some background knowledge, its basic techniques, and to show some examples of its flexibility in controlling the voice characters of synthetic speech. Then I will introduce some recent advances of this method, which were developed by our research group. I'll give 3 examples. The first is the articulatory control of HMM-based speech synthesis. The second is minimum care divergence parameter generation. And the third one is the hybrid HMM-based unit selection speech synthesis. Okay, so I'll start from some background introduction. So what is speech synthesis? It is defined as a kind of method of artificial production of human speech. And in recent years, speech synthesis has become one of the key techniques in speech-driven intelligent human-machine interaction. If the input to a speech synthesis system is in the form of a text, we can also name it text-to-speech, or TTS for short. It can be considered as a kind of, inverse function of automatic speech recognition. Because in automatic speech recognition, we want to convert speech to text, but in TTS, we do the inverse thing. This figure shows the general diagram of a TTS system, which is composed of 2 main modules. The first one is text analysis. This module converts the input text to some intermediate linguistic representation. For example, we extract the phoneme sequence from the input text, get the word segmentation, some phrase boundary prediction, or some other things. And the next module is waveform generation. By this module, we produce speech according to this kind of linguistic representation. We also name these 2 modules the front end and the back end of a TTS system. And in this talk here, I will focus on the back end techniques of a TTS system. That means when I mention speech synthesis in the following introduction, that only refer to the back end of a TTS system. So in order to realize a speech synthesis system, many different kind of approaches have been proposed in history. Before the 1990s, the rule-based format synthesis is the most dominating method. Here, format means some acoustic features which describe the resonant frequency of a speech spectrum. In this method, we have each phonetic unit. We have the format features of each phonetic units designed by human beings manually using some rules. and the final synthetic speech is produced using a source field model. Then, after 1990s, the corpus-based concatenative synthesis become more and more popular. Here, corpus means a large speech database with some recording speech waveform and necessary label information. In this method, we concatenate the segment of speech unit or speech waveform to construct an entire synthesis sentence. There are different kind of implementations. In some methods, we have only one instance or one candidate unit for each target unit. So that's the single inventory method. More method, we have multiple instances for each candidate, for each target unit. That means we need to do some unit selection to select the most appropriate unit to synthesize the target sentence. Then, in the middle of 1990s, another method what has been proposed, that is the corpus-based statistical parametric synthesis. In this method, we estimate acoustic models automatically from the large training data set. Then, at synthesis time, we will predict the acoustic features from the trained acoustic models, and then using some kind of source field model to reconstruct the speech waveform. So this method can have better flexibility compared with the previous waveform concatenation method. And in most cases, hidden Markov model is used as the statistical acoustic model. So we commonly name this method the HM-based speech synthesis, or HTS for short, which means triple S. We can see the 3 S letters here. So in this talk, I will introduce this kind of method, including some basic techniques and recent advances of HM-based speech synthesis. Before I introduce the basic techniques of this kind of HM-based speech synthesis, I'd like to show the overall flowchart of this method. We can see that the HM-based speech synthesis system can be divided in 2 parts. The first one is the training part. The second is the synthesis part. The training part is very similar to the HM-based automatic speech recognition. We firstly extract acoustic features, including the excitation parameter and the spectral parameter from the speech waveform of the pre-recorded database. Then we train a set of hidden Markov models using the extracted parameters and the label information of the database. At the synthesis time, the input text first passes through a text analysis module to get this kind of label information, which is just the linguistic representation we mentioned above. Then we generate the acoustic parameters, such as the excitation parameter and spectral parameter, from this HM model set according to the label information. Finally, these parameters would be sent into a source field model to reconstruct the speech signal. So this is how a HM-based speech synthesis work. There are 4 very important techniques to HM-based speech synthesis. I'll give some more detailed introduction to them one by one. The first technique is speech vocoding. Speech vocoding means at the training time, we extract acoustic features from the speech waveform, and at the synthesis time, we reconstruct the speech waveform from the predicted speech features. The speech vocoding techniques is motivated by the speech production mechanism of human beings. We can look at this figure here. When people speak, we'll first have this airflow produced by lungs. Then this airflow will pass through the vocal cords to generate the source signal of the speech. When we pronounce a vowel segment or a vowel, our vocal cords will vibrate periodically, and so we can get a pulse trend as the sound source. When we speak some unvoiced speech segments, for example, some consonants, our vocal cords would not vibrate, so we get some noise-like sound source. This pulse trend or noise signal will pass through the vocal tract and generate the final speech. The function of vocal tract is very similar, like a filter. Its frequency transfer characteristics will decide which specific phoneme we are pronouncing. So mathematically, we can construct a vocoder using this kind of source filter model. It consists of a source excitation part and a vocal tract resonance part. In the source excitation part, we have the excitation signal En, which is either a pulse trend or white noise. And in the vocal tract resonance part, we use a linear time invariant filter Hn to represent the vocal tract character of each speech frame. So the final speech is a convolution between these two signals, En and Hn. Furthermore, we will extract some spectral parameters to describe the vocal tract system Hn or its Fourier transform. Here we can use different kinds of spectral parameters just according to the different kinds of speech spectral model we used. For example, we can use the autoregressive model to represent the speech generation process. In this case, the speech parameters, the spectral parameters Cm would become the linear prediction coefficient. We can also use some exponential model. In this model, the spectral parameters Cm would become the capsule coefficients. Anyway, we can estimate these parameters by some maximum likelihood criterion, like this equation here. The observation vector O means the speech waveform of each speech frame, and C is the filter coefficient we want to estimate. Here, this figure shows summarizes how the speech vocoder work at synthesis time, at training time, and at synthesis time. At the training time, we extract the acoustic features such as the F0 and unvoiced voice, the label information, and the male capstrum from the original speech frame by frame. Then these speech parameters will be modeled by hidden Markov model in the next acoustic modeling step. At synthesis time, all these parameters will be generated from the trained acoustic models and sent into the speech synthesizer to reconstruct the speech signal. So that means we use speech vocoder to extract acoustic features at the training time and reconstruct the speech signal or speech waveform at the synthesis time. The next technique that's very important to the HM-based speech synthesis is the speech parameter modeling and generation. Here, hidden Markov model is used as the acoustic model to describe the distribution of acoustic features. This figure shows an example of hidden Markov model, which has 3 states and left to right topology. Here, the O and Q stands for the observed acoustic feature sequence and the hidden state sequence for each sentence, and the BQOT is the state output probability at each state, and the A is the state transition probability. Then the model training of HM-based speech synthesis is just the same as HM-based automatic speech recognition. Here we estimate hidden Markov model for each phonetic unit. For example, for each phoneme, we can do it by following the maximum likelihood criterion and using a EM algorithm to update the model parameters iteratively. Then, at synthesis time, assume the hidden Markov model for the target sentence is given. So our task is to generate speech parameters from this model. The method we use is to determine a speech parameter vector sequence by maximize the output probability in this way. Here, lambda is the H model of the target sentence, and O is the acoustic features we want to generate. We can firstly approximate this equation by using only the most popular state sequence replace the summation over all possible state sequence. Then we convert it to a two-step optimization problem. The first step is to predict the hidden unit sequence independent from the acoustic feature sequence. We have introduced that in our method, we use the HM of the left to right topology. So that means if we want to determine the state sequence of a hidden model, which is the same as to determine the duration of each state. So at training time, we estimate the state duration distributions for each state, which is the PI function. Then the state sequence Q can be predicted for an input sentence by maximize this output probability. If we use a single Gaussian to describe this distribution, then the output will just be the mean of this Gaussian. So it's quite simple. The next step is that when the optimal state sequence Q has been determined, we want to generate the acoustic feature sequence O. It's also based on the maximum output probability criterion. We can have a look at this figure, which shows an example of parameter generation from a sentence hidden Markov model. Here, we can see that each vertical dotted line represents a frame, and the interval between two solid lines, for example, between this one and this one, is a state. So we can see that different state has different durations. Here, the red line shows the mean of the Gaussian distribution for the state output probability, and the pink area shows its variance. It's obvious that if we want to generate the acoustic feature O, which maximizes the output probability, the O would become a sequence of the mean vector, just this stepwise shape. But it will cause a problem, which is the discontinuity at the state boundaries. It will, if we just reconstruct a speech signal using this kind of output, the quality of static speech will degrade because of some discontinuity in the speech waveform. So we solve this problem by introducing some dynamic features into the acoustic model. Here, CT is the static acoustic feature at frame T. And we can calculate the delta CT and the delta square CT as the delta and the acceleration features. Here, the delta and the acceleration features are corresponds to the first and second derivative of the static acoustic feature sequence. They are just a kind of, can be considered as a kind of linear combination of the static features at neighboring frames. Then we can put the static and dynamic feature together, for example, in this way, to get the complete speech parameter vector OT. If we look at a whole sentence, we can see that the complete acoustic feature sequence O can be considered as a kind of linear transform from the static feature sequence C with the transform matrix W, which is determined by how we define the dynamic features. Then we can rewrite our parameter generation criterion in this way. So that means we want to find the optimal static feature sequence C to maximize the output probability of the complete acoustic feature sequence O, which contains both the static and the dynamic components. So by setting the derivative of this function with respect to C to 0, we can get a solution of this problem. We can solve the C after solving this group of linear equations. Its computational complexity is not very high because the W is a very sparse matrix here. This example shows this figure shows what will happen if the dynamic features are used. We can see that under the constraint of dynamic features, the generated acoustic feature, here is the blue line, will become much more smooth compared to the stepwise, the red line, the stepwise the mean sequence. Subjective evaluation results have proved that this kind of parameter generation algorithm is very effective in improving the speech quality or the naturalness of synthetic speech by reducing the discontinuity at set boundaries. Okay.
So is there any, after you finish that the solution, is there any property for the generated curve? For example, it doesn't actually oscillate too much. In principle, things can move, right?
Yeah.
But most things is smooth. So what part of the solution that can guarantee that?
You mean no fluctuation or something?
Yeah.
Because this figure does not show the whole story. It only shows that we have the first derivative.
But in practice, I've never seen any oscillation here.
Yeah, because here, actually, if we only using the first order derivative, there may be some fluctuation.
Oh, you can see that fluctuation?
Yeah. That's how we calculate the dynamic features, because the first derivative only use the next frame and the previous frame.
Okay.
So there will be some fluctuation. If we use the first order and the second order together, okay, we can guarantee the smoothness of the without fluctuation. So the next techniques that's very important for HMM-based speech synthesis is the MSD-HMM for S0 modeling. I have mentioned above that in speech vocoding step, we will extract not only the male caption but also.
Can you go back to the previous slide?
Okay.
So where one more slide before? Where is the variance for the delta prime? Oh no, because the sigma contains all the streams together, right?
Yeah, that contains
so that's the 3m dimension, not just one sigma.
No.
Okay, I see. Okay, so that's what. So all the variables are taken including the delta prime variance.
So in hidden Markov model-based speech synthesis, it's also very important to predict the F0 features. The F0 means the fundamental frequency. It decides the pitch of the synthetic speech. This figure shows the example of the trajectory of the observed F0s. We can see that there is a very important property of F0, that is, F0 only exists in the voiced segment of a speech, for example, this segment. For some unvoiced segment, we cannot observe the F0 at all. So that means we cannot just apply the continuous or discrete HM to modeling the F0 directly, because in some part of the F0 trajectory, it has no observations. Here, a new form of hidden Markov model has been proposed, which is named the multi-space probability distribution hidden Markov model to solve this problem. And this figure shows the structure of a multi-space probability distribution hidden Markov model. We can see that each state can have two or more distributions to describe the acoustic features. It's very similar to the multi-mixture hidden Markov model, for example, using Gaussian mixture model for each state. But the difference is that for each state, here in MSD-HMM, we can have different dimensions for different mixture. For example, this component maybe have dimension 1, this maybe dimension 2 dimension. Some distributions have 0 dimension, which means only a discrete value. So it provides more flexibility than the multi-mixture hidden Markov model. If we apply the MSD-HMM to F0, we use this kind of model structures. We use two space. The first space is a one-dimension continuous value, which is modeled by a single Gaussian distribution. The second space is of 0 dimension, which means it just presents the unvoiced space without observations.
That means it's just binary.
Yeah. Actually,
1 or 0.
Here we only use weight to represent the unvoiced space. These two weights, how to stand for the probability of the current state being voiced or being unvoiced. They also need to be trained according to the training data.
Voice, then you get distribution on the F0.
Yeah.
So if there's no voice, you don't have the parameter, you just have separate.
Yeah, actually for each state, we have these two distributions. They are just to be decided, whether or not it's voiced or unvoiced is decided by the weight. For example, for a vowel, this weight will be very close to 1, and this weight is very close to 0. So it provides this kind of flexibility.
Yeah, so in that case, voice unvoiced detection is built automatically into the model. So do you have to separate voice and unvoiced?
For the training data, the voice and unvoiced features need to be extracted for each frame.
For the training set.
Yeah. But
this
in the feature extraction, we need to decide each frame to be voiced or unvoiced. But in the model training, we do not need to we do not need to decide each state to be voiced or unvoiced.
I see. Okay.
We can assume that there are two spaces in each state, so it can be trained automatically.
I see.
So let me have a look at this figure. This figure shows the final complete acoustic feature vector we used in our model training, which is composed of two parts. The first is spectrum part, the second is excitation part. The spectrum part may consist, for example, the static delta and delta male capture coefficients. We can using a multi-dimensional single Gaussian to model it for each HM state. In the excitation part, it consists of the static delta and the delta log F0. For each dimension, we use a two-space distribution to modify the F0.
So altogether, you just have several streams.
Yeah, altogether here we have 4 streams. The first stream is for the male capture, and the 3 other streams are for the different components of the excitation.
So they are independent when you run them, as if they are separate from each other.
Yes.
So do you have to constrain them, saying that this one has to align with this?
Yeah, they need to be aligned at state boundaries. Yeah. But there is no dependency between these streams. So the last technique very important for HM-based synthesis is the context-dependent model training and clustering. In HM-based synthesis, we expect to estimate the hidden Markov models as accurately as possible to describe the distribution of acoustic features. So that means we need to take into account the factors of speech variations. Here we use the context information to represent this kind of factors. So that means we will train different HMs for the phonetic units with different contexts. So we got this kind of context-dependent hidden Markov model. The most simple form of context is the phone identifier. For example, we train a hidden Markov model for different phones. If there are 60 phonemes in English, we got 60 hidden Markov models. But we can do it further. For example, here we can see a phone sequence of a sentence. There are several instances of the same vowel. But we can use different kind of model to represent each sample because their surrounding or their neighboring phonetic environments are different. So that will lead to we call it the triphone model.
So CL means closure, right?
It's just, I think this is a
closure.
It's a phone transcription of Japanese, maybe.
Japanese. I see. Okay.
So actually, in HM-based business, we need to take into account a very large number of content information. They can be at different levels. At phoneme level, we need to consider the current phoneme and the neighboring phonemes. In syllable level, we need to consider the position of the phoneme in a syllable or something like that. In word level, maybe we need to consider the part of speech or some other content information. At the phrase level, we need to consider the phrase boundary or boundary tone or some other things. So if we combine all this kind of content information together, we will get a very huge number. So it will definitely lead to the data sparsity problem. That means for each content-dependent model, we can only find one sample or even no sample in the training database. So how to solve this problem? We just use a simple method. That is, we allow the context-dependent hidden Markov models to share their parameters if their context information are similar. In order to decide the strategy of model sharing, the distribution-based state clustering method has been popularly used. This is a kind of top to bottom method. At first, we assume all the states of hidden Markov models, context-dependent hidden Markov models, share their distribution parameters. Then, at each state, each state will be separated automatically by find the optimal question. Here, the questions, for example, are here. They are selected from a question set, which is predefined according to the context descriptions of different language, and the optimal question is determined by the maximum likelihood criterion with some pooling consideration. So after the decision tree has been constructed, all the context-dependent hidden Markov models in the same leaf node will share their parameters. For example, all these HMM will have, all these state distributions will have the same mean and the same variance. At synthesis time, the input text first pass through a text analysis module and get the content information of the target sentence. Then this kind of content information will be used to answer the questions in the decision trees, and finally we can get the decision tree, the leaf node of the decision tree, which represent the distribution parameters of each synthesis states. Then we can concatenate the states together one by one to get the HMMs for each phoneme. And furthermore, we concatenate this phoneme together to get the HM of the whole sentence. Once the HM of the whole sentence are given, we can use the parameter generation algorithm, which we have introduced before, to produce the speech parameters.
Yeah, but this is if they have to be consistent, right? So if the right for the previous state chosen, then the next state should have the left context. So are they ensured?
Yes, I think because this content information are decided by the input sentence, they are the text analysis results of the input sentence. So I think that should be consistent with just this.
But the example isn't consistent.
Oh, okay.
It's just randomly choose that one.
Yeah.
But in practice,
that's
you put the consistent.
And another thing I want to mention here is that in HMM-based speech synthesis, because we use multiple acoustic features. For example, we build the statics model for Markov spectrum, for F0, and for static durations. And different kind of acoustic features are affected by different kind of content information. For example, the phone identifier or phone category will be more important to Markov spectrum, but the stress or accident information is more important for F0. So in our implementation, we built the stream-dependent decision trees. That means for the Markov spectrum, for F0, or for static duration, we have different decision tree to have better modeling to the different kind of acoustic features. After the above introduction, we have see that what the HMM-based speech synthesis is and some basic techniques of this method. That is a very important advantage of the HMM-based speech synthesis, that is its flexibility. We can see that different from the waveform concatenation method. In HMM-based speech synthesis system, we do not use the speech waveform directly at synthesis time. We just predict acoustic features from acoustic model, which means we can control the voice characteristics of synthetic speech flexibly by just modify or changing the parameters of acoustic model. Here, I will show you several examples of the flexibility of HMM-based speech synthesis. The first one is we call it adaptation. That means we can build a synthesis system of the target speaker or of different speaking style with only a small amount of training data from this speaker or style. The techniques we used in model adaptation originally developed in SR, speech recognition, but that works well in the TDS. Here, I can show you some examples of the speech adaptation results. At first, I'd like to play the original voice of a recorded speech.
Author of The Danger Trail, Philip Steele's, etc.
This is from a female speaker, the recorded speech. And we can train an average voice model here using a multi-speaker database and synthesize the speech. It sounds like this.
I wish you were down here with me.
So maybe it does not sound like anyone, just average voice. If we have 10 sentences from the target speaker, we can use this amount of data to adapt the average model, and we can generate a adapted model and synthesize the speech in this like this.
I wish you were down here with me.
We can perceive that it's very much more close to the original voice of the female speaker. If we have more sentences, we can do it better. This is the 100 sentence results.
I wish you were down here with me. I wish you were down here with me.
More than 1,000.
I wish you were down here with me.
You can compare it to the original voice.
Author of The Danger Trail, Philip Steele's, etc.
I think it's very close to the original voice compared to the average voice. So the next example is we call the interpolation. That means if we have some representative hit mark model sets, we can interpolate their model parameters to gradually change the speaker and the speaking styles. For example, we can do the speaker interpolation to realize a transition from a male speaker to a female speaker. Here I can show you how the synthetic speech is affected by the interpolation ratio. This is a male speaker's synthetic voice.
I wish you were down here with me.
This is a female speaker's.
I wish you were down here with me.
If we use some interpolation ratio, we can perceive the transition effect of the voice.
I wish you were down here with me.
I wish you were down here with me. I wish you were down here with me. I wish you were down here with me.
And if we have many representative HMM sets, then it will cause a problem that is very difficult to set. The.
So when you do interpolation, that means you interpolate all the means for each state?
Yes.
Yeah, but how do you know which one? Oh yeah, because you have the phoneme already. So for the corresponding context-dependent phone, you do interpolation.
Yeah, they're just the same contact information we do the interpolation.
I see. And how about the pitch?
Do the same thing. We can.
As well?
Yeah,
the mean of the pitch.
Yeah. And the variance.
Okay.
In this example, we can also perceive the transition of pitch. From male, we have a lower pitch, but the female has higher pitch. We can see it's become higher and higher. Yeah. This is the eigenvoice method. In this method, the motivation is that when we have a large number of representative hit mark model sets, it's very difficult to set the interpolation ratio for each HMM set. So we just treat each HMM set as a supervector and apply PCI analysis to reduce the dimensionality of speak space. Then we can control the voice characteristics simply. The last example is multiple regression hit mark model. In this method, we can assign an intuitive meaning to each eigenspace dimension. For example, in emotional speech synthesis, we can give each dimension of the eigenspace some meaning. For example, this one means sad, this one means joyful, this means rough. Then we can control the emotion category of synthetic speech by using a 3-dimension emotion vector. It will be more easy to much easier to control the emotion of synthetic speech. Okay. Before I finish the first part of this talk, I'd like to recommend some resources which are very useful for HMM-based speech synthesis. The first one is the HTS toolkit for HMM-based speech synthesis. It can be obtained from this website. And this is a software reciprocal platform for HMM-based speech synthesis. It's released as a patch code for HTK. And it also provides some demo scripts. So if you have your own training data, it's very easy to construct a speech synthesis system by your own. The next resource is the HTS slides. It's just, I think it's very useful tutorial to the researchers who are interested in this topic. And some of the slides here are also adapted from this material. Okay. In the second part of my talk, I'd like to introduce some recent advances of the hidden Markov model-based speech synthesis, which were developed by our research group. The first topic I'd like to introduce is the article control of hidden Markov model-based speech synthesis. Here, we have introduced that in the conventional hidden Markov model-based speech synthesis, we train content-dependent hidden Markov models for acoustic features. These acoustic features are extracted from the speech waveforms. At the same time, we use this kind of parameter generation algorithm to predict the acoustic features and to reconstruct the speech waveform. There are many advantages of this method. For example, it's very flexible, it's trainable, and we can do some model adaptation to change the character of synthetic speech. But there are some also disadvantages of this method. One of the limitations of HM-based speech synthesis comes from that it's a data-driven approach. It constrains that the character of synthetic speech is strongly dependent on the training data available. And it's very difficult to integrate the phonetic knowledge into the system building. For example, if we want to build a voice of a child, so that means we need to collect some data from a child in advance, no matter you are doing speaker-dependent model training or model adaptation. But on the other hand, we may have some phonetic knowledge which can describe the difference between an adult's voice and a child's voice. For a child, the vocal tract is much shorter and the formants are much higher. But in HM-based speech synthesis, it's very difficult to integrate this kind of, we name it, phonetic knowledge into the system building. So we use another kind of feature here. It's named articulatory feature. The articulatory feature describes the movement of articulators when people speak. They can provide a simple explanation for speech characteristics, and they are very convenient for representing the phonetic knowledge. This kind of articulatory features can be captured by some modern signal acquisition techniques. For example, in our experiment, we use the electromagnetic articulographer to capture this kind of articulatory features. In this technique, we attach some very tiny sensors onto the tones and the lips of the speaker during his pronunciation. Then we can record the real-time position of all these sensors when he speaks. Because of these advantages of articulatory features, we propose the method to integrate this articulatory feature into hidden Markov model-based speech synthesis to further improve its flexibility. At the training time, we estimate a joint distribution for the acoustic and articulatory features extracted at each frame, just this one. Here, X denotes the acoustic feature and Y denotes the articulatory feature. If we look at the state of output probability, we model the cross-stream dependency between the acoustic feature and the articulatory feature explicitly. This is because of the speech production mechanisms. We know that the speech waveform is always caused by the movement of your articulators. So we model this kind of dependency. At synthesis time, the process is a little bit more complex than the conventional method. When the unified acoustic and articulatory model has been trained, we first generate the articulatory features at the synthesis time. Then we design an articulatory control module by integrating the phonetic knowledge and to affect the final generated acoustic features. In terms of the cross-stream dependency modeling, we have proposed two different kind of methods. The first one is the content-dependent transform tiering. Here, we can see here this conditional distribution just describes the relationship between acoustic and articulatory features at each HM state. Here we use a linear transform from the articulatory features YT to determine the mean of the distribution for acoustic features. This AT is trained. This AG is trained for each HMM state, so it may have some disadvantages. For example, it cannot adapt to the modified acoustic articulatory features. Because at synthesis time, we will generate the YT at first, then we will modify it.
Yeah, but in that case, for the training time, you need to simultaneously collect the articulatory information,
Yes.
the EMA information directly on the same speaker.
Yeah.
And that's a very expensive process.
Yes, of course. It's very expensive and difficult.
To do that. So
Yeah.
you build the model, the question is how do you generalize that to another speaker in the test time? Right? So when you do adaptation, do you need to articulate feature at the same time?
The model adaptation is still, we haven't finished model adaptation now.
Okay, so
We only focus on the single speaker till now. In the next step, we are trying to find some maybe more feasible approach to do the model adaptation for this kind of modeling.
That's very interesting, yeah, because now here you're assuming the dependency to be linear, but in practice, it's very, very highly nonlinear.
Yeah,
right?
actually here, the AG is state dependent, so globally it's kind of nonlinear. In other words, piecewise linear transform.
So I have actually the same model that I have been doing for a few years. It's looks just exactly the same as for recognition.
Okay.
So you infer, you treat that Y to be hidden variable, and then you integrate them up, and then from that you can infer the state that you can do using verb recognition. So
Yeah.
very, very, very curious to know, how good this is.
Yeah. And we also improved the previous model structure, and we developed a feature space transformatory method. In this method, we at first train a Gaussian mixing model, a lambda G, to represent the articulatory feature space. Then we train a group of linear transform, but the linear transform A is not estimated for each HMM state, but estimated for each mixture of the Gaussian mixture model. That means when we modify the articulatory feature YT at the synthesis time, this posterior probability will change accordingly, and then that will affect the relationship between Y and X, so we can get a better representation of this kind of relationship at the synthesis time.
This is the same question here. Since you treat this Y to be hidden variable, right? You don't need to have data in the training, right? It's just EM algorithm.
Yeah, but yeah.
So why do you need to have?
But in our framework, the Y is not treated as hidden variable. We think they are observable.
But according to this model,
Yeah, that
it's
could
hidden
be.
variable, huh?
Yeah.
So have you tried anything to make that, interpolation approach, right? So the question is that without that articulate, so assume that since you do have that articulate feature data, you can use it to initialize model.
Yeah.
And then on top of this, you can do EM.
Yeah.
You may do better. Do you have that one?
We haven't considered it because in our at synthesis time, we need to generate Y, and then we need to modify it. Yeah, we need to generate Y because the motivation of our method is that.
Can you go back to see how is the generation process?
Okay,
synthesis process is.
So it's like this way.
Okay.
We first generate the articulatory features. The reason is that we think articulatory feature is more physically meaningful.
So doing sampling. Do you do sampling?
No, just also the maximum output probability parameter generation.
Okay, so you got the delta parameter for Y.
Yeah, of course, yeah.
Okay. So once you have that, then how do you get? But I thought that you model them jointly, right? X and Y. So you can do that together.
Yeah, we can do it together. But at synthesis time, we want to integrate this kind of phonetic knowledge.
For example, you modify.
Yeah, we think it's more feasible to
to
do this kind of control for articulatory features than for acoustic features.
All this can be done by machine learning technique, just doing the standard. I think we will talk about that later.
Okay.
So this is a very kind of stage by stage, not okay. We'll talk about it later. Okay.
So here I can show some experiments results. We use a English database because the recording is expensive, so we have only more than 1,000 sentences. But that's enough for a speaker-dependent speech synthesis model training. We use 6 sensors, and it has 2 dimensions.
Yeah, so you have EMA data for all these 1,000 sentences?
Yes.
Oh, that's good.
And I think this database is a public.
It's a public database?
Yeah. Every researcher can use it for some research progress.
Okay.
Just search this name. We can. I think there is a website for this database now. The first experiment is some hyperarticulation experiment. That means we want to simulate that in some noisy conditions, the speaker may want to put more effort when they pronounce. So they will open their mouth wider or something like that. So we just, in this experiment, we generate the articulatory features at first. Then we modify the articulatory features using a 1.5 scaling factor for the Z coordinate. Z coordinate means the bottom to up direction. We just want to simulate that when you pronounce, your articulators move in a much larger.
Can you take a look at the mouth? Yeah, three slides ago. Back. Yeah, back. One more.
Back. Okay.
One more. Yeah, this one.
Yeah.
So when you want to simulate to synthesize hyper-articulated one, you're saying that you move all the Z dimension up.
Yeah, a wider range.
Wider range. I see. So including all this 1, 2. How many dimensions you have? 1, 2, 3.
We have
4,
6
5.
sensors. Each sensor we use 2 dimensions. That is Z and Y, because all these sensors are put in the middle. So the x-axis is omit. So we use these 2 dimensions, and in the first experiment we just scaling up the Z dimension.
Yeah, but it's very dangerous. Right? If UL, that's upper labial or feature, is moving up, the mouth can open. In that case.
Yeah, I think it's just some. This modifying rule is a little bit heuristic. Yeah, we just want to simulate whether or not this kind of modification on articulatory features can influence the generated acoustic features.
So this is by what? So what do you mean by the articulatory control? You simply just manipulate them by knowledge. Right?
Yeah.
And then you are going to see how it looks like.
We have some, maybe the knowledge is not very. How to say? It's not very in detail. We just know. Yeah.
So, but why is it that when you move Z dimension up, it's going to be hyper-articulated? It's not obvious from the.
We not only move it up, we just move. The range. We increase the range.
Oh, I see.
Increase the range.
So in your system, you just make the variance bigger.
Yeah.
That's all you do.
Yeah. That's what we have done.
So not learn them, but artificially manipulate them.
No.
Okay, I see. Okay, that's good.
Yeah, so we can see some changes in the speech spectrogram. We can see that after this kind of modification, the phonemic structure become more clear, and the high frequency part get more energy. And also, we did a subjective listening test for the listeners to do some dictation in some noisy conditions at 5 dB SNR, and we can see that the word error rate drops from 52% to 45.
How do you speech recognition again? I don't understand.
No, this is dictation of synthetic speech.
Oh, I see. So you use that to generate that.
Yeah.
Oh, I see. Okay.
We synthesize some speech and ask the listeners to write down the words that they heard.
Oh, it's for human listening.
Yeah, human listener.
What error rate?
Yeah, the word error rate of human dictation.
I see.
Human dictation. Yeah.
Okay.
We just want to improve the intelligibility of the synthetic speech in noisy conditions.
Yeah, that's very hard to believe, right? Because all you do is that you increase the variance of Y variable, right?
Yeah.
And then when you do that, why does the formula move up? But do you also have to estimate this A?
Yeah.
The transfer matrix.
That means I think the reason is there are some by using the conditional distribution here, for example.
Yeah. It's just not.
For example, this way we can learn some relationship between acoustic and articulatory features. There are some training samples in the database with the large variance of your tongue movement. So we can learn this kind of relationship. That means if your tongue movement is has a wide range, so what your acoustic representation would be. There are some samples of this in the training data. We can learn this by this dependency. At synthetic time, we can.
That's how you learn A, right?
Yeah, this
so
is.
You artificially increase the variance for Y.
Yeah.
is learned differently.
Yeah.
Otherwise.
A has been learned from the training database. At the synthetic time, we generate Y at first, then we increase the variance of.
A is kept the same.
A is the same.
Kept the same.
Yeah.
Oh, okay. That's very interesting.
And the second example is the vowel modification. And in this experiment, our phonetic knowledge is the place of articulation for different vowels. We can look at this this table here, there are some vowels in English, for example, the vowel A, vowel E, or vowel A. The most significant difference between these vowels, among these vowels, are their tongue height. For the E, we have a higher tongue, and the A have a lower tongue. A has a middle tongue. So here, we just predict the articulatory features using the vowel A at first. Then we modify the height of these three sensors on our tongues to see whether or not we can change this vowel to be perceived as vowel E or vowel A, respectively.
Oh, so what it means is your learning must be really good for A. Otherwise, you won't be able to capture the potential.
Yeah, but here we have some very, how to say, positive experiment results. For example, when we increase the height of the tongue, most of the stimulus will be perceived as vowel E here. If we decrease the height, most of them will be perceived as A.
Oh, that's done by human.
This is a human perception, also the dictation results. Here I can show you some examples of the synthetic speech. This one is the synthetic speech for the vowel A. This is a sentence, carrier sentence with the word set. We can hear that.
Now we'll say set again.
That's a set. If we increase the tongue height,
Now we'll say set again. Now we'll say set again. Now we'll say sit again.
now it becomes sit. I think it's a very clear transformation.
Now we'll say sat again. Now we'll say sat again. Now we'll say sat again.
Yeah, become more like that.
Yeah. So by this experiment, we show that our...
You know that, I mean, the difference between those are more than just the formats. They also depend on duration. Right?
Yeah.
Like sad become duration.
Yeah.
So somehow, that's very interesting.
Yeah.
But I just can't believe that it's going to be so powerful. All you do is you do linear transformation. Right?
Linear transformation in the articulatory feature space.
Yeah, correct.
But in the modification are in the articulatory feature space.
Correct.
We just mod some simple modification. But in the
So it sounds like when you move that through the linear transformation,
Yeah,
the
yeah.
format is going to move.
yeah.
That's not obvious. Yeah, okay. So.
But here I have said that the linear transform is estimated for each state or each Gaussian mixture or each subspace of articulatory features. So totally we have a nonlinear transform.
I see. Okay. So you actually just, in that case, you move the mean.
Yeah.
What, right?
Yeah.
The
Here.
mean of the y. So tell me. So what exactly? You get 6 dimensions, right?
Yes.
And each dimension. So like each 6 sensors, and each sensor has 2 dimensions.
Here
X
we
and Y.
only move these 3 dimensions. Only the 3 sensors on your tongue.
Okay. And
These 3 sensors are not modified, because our knowledge is that only the tongue height.
Okay.
Of
So when you move tongue height, of course, your format is going to change.
Yeah.
So what I heard here is just I'm able to hear that the format actually changes.
Yeah.
I see. So that's consistent from your hyper speech.
Yeah.
Okay. Oh, that's cool. That's really cool.
And also, this is only some preliminary attempt of integrating these kind of articulatory features.
So did you do that in England or did you do that in China?
This is some cooperative research with CSTI Edinburgh.
Oh, Edinburgh.
Yeah.
Okay, I see. Oh,
So this is an English database. The database is recorded by them.
Okay, Edinburgh. Okay.
Okay. The second example I'd like to introduce is the minimum scale divergence parameter generation. We know that in the HMM-based speech synthesis, it has many advantages. For example, it's trainable, it's flexible, it's adaptable. But there is also some disadvantages of this method. The most significant one is the quality of synthetic speech is degraded. We can perceive some, buzz or uncomfortable things in the synthetic speech. So there are 3 reasons which cause this kind of speech quality degradation. The first is the quality of the vocoder, and the second is the acoustic modeling method, and the third is the parameter generation algorithm. Once we use the maximum output probability parameter generation introduced above, it will be over-smoothed. Here we focus on the third cause of this kind of problem. This equation has been introduced before. This is the maximum output probability parameter generation. Because in our methods, the state PDF function is represented by a single Gaussian. So if we solve this problem, the outputs are very close to the sample mean. Even if we have used some dynamic features, they are still very close to the mean of each state. So the detailed characteristic of the speech parameters are lost in the synthetic speech.
So MOPPG stands for
maximum output probability
okay.
parameter generation. Yeah. Just this one. Okay. Many improved methods has been proposed try to solve this kind of problem. I think the most successful one is the global variance modeling. In this method, we calculate the sentence level variance of acoustic features for each training sentence. Then we estimate a single Gaussian distribution, lambda v, for this kind of global variance. Then at the synthesis time, the object function is defined in this way, which is a combination of two parts. The first one is the conventional output probability of the acoustic hidden mark model, and the second one is the output probability of the global variance model. So under the constraint of this model, we can generate the acoustic feature trajectory with larger variance and improve the to alleviate the over-smoothing of the trajectory and improve the quality of synthetic speech.
So why don't you just, after you do the training, you just increase the variance by a certain amount?
You mean at synthesis time or?
Yeah, in synthesis time.
Yeah, but I think that's too heuristic. Yeah. Here we guided it by some static model.
Okay. So you train that part.
Yeah, this is trained.
Okay.
This is trained. For each sentence we have a global variance.
After you do this kind of training, do you see the amount of change in the variance?
Yeah.
Are they consistent across different phones, different states, or are they, some states may increase more?
I think that's, according to this criterion, I think this kind of variance increment should be inconsistent because there is a trade-off between these two parts.
Yeah, so we call that regularization.
Yeah.
You put the term there to penalize.
Yeah, something like that. Yes. And this method has been proved to be very effective. In some experiments, it can improve the quality of synthetic speech significantly.
That's one question. There are so many other regulation methods you can do. Why do you choose that particular one?
I think maybe depends on the problem, because here over-smoothing is the most important problem. We want more variation in the synthetic speech. And another method is the parameter generation method based on segment-wise representation. Here, the output probability is calculated using the mean of the generated segments instead of the output probability of each frame. We just use the mean to calculate the output probability. We can see that there is a common point of both these two methods. That is, both these two methods examine the similarity between the distortion parameters trained on natural speech and this parameter derived from the generated acoustic features. For example, in the GV method, the distribution parameter is the sentence level variance. And in this method, the distribution parameter is the state level or segment level mean. We want this kind of distribution parameters to be similar for both for the natural speech and for the generated speech. So based on this, we proposed another kind of parameter generation algorithm, which is in this method we explicitly measure the distribution similarity between the generated feature and the natural feature. Here, the generated hidden mark model, which means the sentence HM estimate from the generated acoustic features, is expected to be as close as possible towards the target HM, which is the HM used for parameter generation. This is the most important criterion in our proposed method. And the KL divergence is adopted to calculate the distance between these two hidden mark models. And we have implemented two approaches to using this criterion, which is to optimize the generated acoustic parameter directly and or to estimate a linear transform to the maximum output probability parameter generation results. So the first thing is that when we generate a sentence from the hidden mark model, we need to estimate the generated HM according to this sentence. It's not easy because we have some data sparsity problem. We have only one sentence we need to estimate HM. Here we use a maximum posterior Western posterior estimation to estimate these HM parameters. And for the mean and the variance of each state, they can be written as a function of the O. O is the generated acoustic feature. That means when the acoustic features are generated, we use these features to estimate the mean and the variance of each HM state, and then get the sentence HM of the generated speech. Then we can calculate the KL divergence between these two HMs. We use the KL divergence in a symmetrical form between the target HM and the generated HM. But unfortunately, because of the hidden state, we cannot calculate this.
Can you explain the target HM versus generated HM?
Okay, right here. We can look at here. The generated HM means the HM estimate from the generated acoustic features. For example, at the synthesis time, we input a text and we generate acoustic trajectory for this sentence.
As you said, it could be too smooth or something, or the problem.
Yeah. But we can estimate a hidden Markov model from this trajectory.
Okay, yeah, which is not very good.
Which
compared with the real.
Yeah, we don't very good, but we want to minimize this distortion.
I see. Okay.
The targeted HM can be considered as the HM that generates the acoustic features.
So now you sort of estimate a new set of HMM that minimize the KL divergence between the two sets, and then you get a third one.
Yeah.
And you can iterate it doing that.
Yeah, something like that.
Until it becomes smaller.
Yeah.
Okay. Oh, that's cool. Okay.
That is something like we.
Sorry. So why do you want to do that instead of just doing sampling?
I think the reason is that here. I think the motivation is that the conventional maximum, the over-smoothing effect of the conventional maximum output probability parameter generation algorithm. If we just use the this kind of output probability to evaluate this sequence is good or not good, then it will cause some over-smoothing problem.
Right. In this case, you only use the mean.
Yes.
But if you also use the variance, just like what Tuda did.
You mean the
right? If you estimate the global variance of the sequence, and then you do the sampling according to the mean and this variance, you should be able to get quite a good result.
I think in total method, when the global variance model has been introduced, it also be solved by maximizing this kind of combined output probability. It's still not a sampling method.
So it's not sample, but I mean, but you can do the sampling if you already have the variance.
Yes, we can. But I have read some results of the just simple sampling method, but I think the result is not so good. That means at the current stage, maybe using the mean is much safer than some. It's a little bit dangerous if you have not a good constraint. How to
sampling you cannot do frame by frame.
Yeah.
You have to do the whole segment that way.
level, right?
So you said that you saw Toguda's presentation talking about sampling.
Yes.
Oh, so do they do a segment level sampling?
Segment level sampling.
I see. Okay, maybe you have seen frame-based sampling.
Yeah. It's not so good.
I see. Okay, so this was kind of give you the segmental. Okay.
Yeah, I think in this method we have not touched the problem of whether or not we should do sampling or use the maximum output probability. We just try to improve the maximum output probability method by using a new.
You still use this criterion, but add another localization, which is.
Actually, when the KL divergence.
But when you do KL divergence, you don't use the global optimum. Variance.
No. I think the criterion is just this one.
Okay.
We just try to find the optimal static feature sequence to minimize this kind of
divergence.
The KL divergence.
And the divergence is measured between two HMMs.
Yeah, the divergence
one of them is the generated.
Using the upper bound approximation of the KL divergence between two hidden Markov models, because this criterion is a function of the C, the static feature. So we just try to solve this problem, and we iteratively updating the C by some steepest descent algorithm to get to get the final results. And this is one method how we make use of the criterion. We have also tried another method, that is we constrain the final output acoustic features to be some linear transform of the maximum output probability parameter generation results in this way. And under this criterion, we just estimate the coefficient and the bias of the linear transform. And we hope that by this method we can get more robust estimation of the transform matrix than to estimate the C directly. Furthermore, we can also estimate the linear transform coefficients and bias on the training set, which means we can do it globally at the training set. So it will reduce the computation complexity at the synthesis time. Here, the KL divergence is calculated for all the sentences in the training set and sum up together. And we can estimate the linear transform to minimize this KL divergence.
So this is the part of training, right? So after your training, you get another HMM. And from the HMM, you can generate model.
Yeah, I think this training we only estimate these two parameters. This is separated from the hidden mark model. The hidden mark model will not be changed anymore.
So what's L and H again?
Here we can.
Oh, it's just transformation.
Yeah, just transformation.
Oh, so it's only two parameters to train.
Yeah. I think that's just an alternative method compared to the previous one. Here we just give many freedom to C. It can change anyway, just to minimize this. But here we give some constraint. We require the C to be a linear.
So you don't train HMM doing this? I think it makes more sense to do that, right?
All these methods are only related with the parameter generation part. The model training is, we do not touch that here. Okay. This is only for how we can generate the parameter beta once the model has been given.
I see. But you can presumably use that to train HMM again, right? Because you originally have HMM. Now, the HMM is maybe too smooth away from your data, training data. So you modify your HMM so that becomes close to each other. So that's what I thought.
No, maybe I can go back to how to say, to here. I think, for example, we can consider it in this way. We have a trained HMM model. We just keep it. Then we can generate acoustic features for input text. Then we can estimate the generated HM from these generated acoustic features. Then if we make some modification to the generated acoustic features, then the generated HM will be different.
I see. Correct.
So we can find the optimal acoustic feature sequence. It has a generated HM which is very close to the target HM. The target HM is what we train at the training time, and it's kept always the same. Okay. Here is some experimental results. We compare the 5 methods here. The first is the conventional maximum output probability parameter generation algorithm. The second is the classic GV method. And these 3 methods are proposed method here. The first is the minimum KL divergent parameter generation. Second is the minimum KL divergent feature transform. This one is also the feature transform, but estimated globally on the training set. We can see that this figure shows the average KL divergence of different parameter generation algorithms. We can see that we compare the natural speech, the MLPPG output, and the GV output. We can see that the natural speech has the lowest KL divergence compared to these 2 methods. That means that I think it means maybe the KL divergence is a better criterion than maximum output probability, because in the sense of output probability, this red line is the optimal, but it sounds not as good as the natural speech. And this figure shows the KL divergence of the natural speech and the 2 of our proposed method. We can see that they become very close. And this figure shows some sample trajectory of the spectral parameters. This is for 1 dimension of male capstrum. We can see that the MLPPG output is very smooth, and the variance is very small. But after we apply the KL divergence-based parameter generation, for example, these 2 methods, we can have the trajectory with much more variation. in the synthetic speech. And this figure shows some subjective evaluation results. That is the naturalness evaluation. We have some synthetic samples and ask people to listen to these samples and give them a score from 1 to 5 to each sample, and we calculate the average value. The higher score means better naturalness. We can listen some samples here. This is the maximum output probability parameter generation output.
我想参赛不是专门为了获奖，重在参与，从中学习一些知识，理解什么是爱国，怎样爱国。
I'm sorry for that. This is only Chinese sample, but maybe we can perceive the difference between this one and the next one. If we use GV method, the speech will be much clearer.
我想参赛不是专门为了获奖，重在参与，从中学习一些知识，理解什么是爱国，怎样爱国。我想参赛不是专门为了获奖，重在参与，从中学习一些知识，理解什么是爱国，怎样爱国。
This is our proposed method.
我想参赛不是专门为了获奖，重在参与，从中学习一些知识，理解什么是爱国，怎样爱国。我想参赛不是专门为了获奖，重在参与，从中学习一些知识，理解什么是爱国，怎样爱国。
We also conducted another subject evaluation by a preference test, that is to compare the GV system, the KL divergence feature transform, and the global feature transform method. The final result is that the global feature transform method can achieve better result even than the GV, and the difference is significant in the group of listeners. In the last part, I will introduce another work we have done before, that is the hybrid Hitchcock model-based unit selection speech synthesis. Before that, I'd like to show some review of the classic unit selection algorithm. In this algorithm, the most important thing is that we need to define two cost functions. For example, here we have a target unit, that is the target we want to synthesize, which is decided by the input text, and we have a candidate unit sequence U. Here we have two cost functions. The first one is the target cost, which define how appropriate the candidate unit can be used to synthesize the target unit. Another cost function we named the concatenation cost, which measures how much the discontinuity will be if we concatenate these two samples together. Then the final unit selection criterion can be defined in this way, which is the summation over all the target costs and the concatenation costs, and the optimal unit sequence is selected by minimizing this cost function. Compared with the HMM-based speech synthesis system, the unit selection and waveform concatenation method has its advantages and disadvantages. For example, for unit selection method, because the real speech segments are used at the synthesis time, so it can produce high quality at the waveform level than the HMM-based speech synthesis. This disadvantage we have mentioned before, that it has the vocoder the sound, so it has some buzz, so you feel not so comfortable when you listen to the speech.
So even after you use the KL distance,
I think it can be improved, but
still not
cannot beat this one, because this is the natural speech segment, especially here, right, in some limited domain. It has very high naturalness if you have a good result. But the disadvantage is that for unit selection, we need a large footprint. That means at the synthesis time, we need to store the whole speech database. It's maybe several hundred megabytes or gigabytes or several gigabytes. And it will cause some discontinuity if we put some unit together that shouldn't be. And also it has some unstable quality. That means for some sentences, we can have very perfect synthesis results. But for some sentences, there will be some glitch in this sample, and you will feel very uncomfortable because of these synthetic errors. So in our previous work, we have proposed a HMM-based unit selection method. In this method, we try to integrate the advantages of statical approach in automatic training and robustness, and the superiority of unit selection synthesis in high naturalness of speech. And we want to achieve a trainable unit selection speech synthesis system. This figure shows the flowchart of the HM-based unit selection speech synthesis system. The training part is almost the same as the HM-based speech synthesis I have introduced before. We extract the features and train the context-dependent HM model for each acoustic feature. The difference is that at the synthesis time, we do not generate acoustic features from the model directly. Instead of that, we have a statistical model-based unit selection module to select the optimal unit sequence based on some statistical criterion derived from these models. Particularly, I will, at the model training part, we will first extract some acoustic features. The commonly used features include the spectrum F0 at each frame, the phone duration, the concatenation spectrum or F0 at the phone boundary. And I think this one is maybe not so important for HM-based parametric speech synthesis, but if we want to do unit selection and waveform concatenation, we need this kind of model. And some other models such as syllable level F0 features or some other things. And the model training is almost the same as the HM-based parametric speech synthesis. We train context-dependent models on the maximum likelihood criterion. We use a descent tree-based model clustering to deal with the data sparsity problem, and we use multi-space distribution HM for the F0 and the concatenating F0 model. And this slide shows the unit selection process. Here, assume the content information of the target sentence is C, and we have a candidate phone sequence U to synthesize this target sentence. Then, how to determine which unit sequence we should select? I think this equation is the criterion we used. It can be divided into two parts. The first part just describe the possibility of the candidate unit sequence to be generated by the target content information. And the second part describes the similarity between the content information of the candidate units and the content information of the target units. We also use the KL divergence between two HMMs to calculate this part. So if we put these two parts together, our criterion is that we want to find a unit sequence which has high probability and low KL divergence in terms of the content information. So we can rewrite this formula into the conventional unit selection formulas, including a target cost, a phone level concatenation cost, and a syllable level concatenation cost. We can use the modified dynamic programming search to do the optimization. Okay, and finally, I will introduce the performance of our proposed method in the Blitzer Challenge speech synthesis evaluation events. Blitzer Challenge is the international speech synthesis evaluation events which has been held every year since 2005. Its purpose is to promote the progress of speech synthesis techniques by evaluating the system built using the same database and different methods. The USTC team entered participated this event since 2006, and we adopted the HM-based unit selection method since 2007, and we have some very excellent performance in all the measurement, all the evaluation tests since that year. So let's take the Blitzer Challenge event of this year, for example. This year, we have a very challenging synthesis topic. That is, the speech database we use is not recorded in a recording room, but taken from some internet resources. This is an audiobook speech database which has 4 stories written by Mark Twain and read by an American English narrator. The database size is quite big. It's more than 50 hours. It has imperfect transcription and recording conditions and rich expressiveness. This slide shows the results of the Blitzer Challenge this year.
That's coming from Interspeech in Poland, right?
Yeah, it's from the Blitzer Challenge workshop, okay, together with the Interspeech. Yeah, here the first item of the evaluation is the similarity, which measures how similar your synthetic speech is towards the voice of the source speaker. We can see that here the A is the natural speech and the C is our system. The mean operating score is about 4.1. It's is the highest score of all participants. And this is the naturalness score. Our system also gets the highest mean operating score, which is about 3.8. In intelligibility, we did some human dictation for the synthetic speech, and the dictation word error rate of our system is around 19%, which is also the lowest of all the systems. This year, we also have some paragraph test. In this test,
sorry, so what is the F? Which is F?
Sorry?
Which group is F?
If I can't remember, actually, this competition is did in a anonymous way. Yeah.
So how do you know that's you?
The organizer will give you later so that you know which system is yours, but they will not tell you. I think I read it. We got some information from the Chinese workshop, but I forgot which F stand for.
I see. Okay. So what is that must be under noisy condition, or otherwise error rate cannot be so high, 20%.
No, it's not a noisy condition. Yeah, because this sentence that we name it SUS sentence. That means semantic unpredictable sentence. Yeah, it's much difficult. You cannot use some content information to guess what the word is. So it's much more difficult.
Okay, that's
So
cool.
can you go back 2 slides?
Mm-hmm.
One more.
Okay.
So FIB performs similarly, right?
Yes, but there are also a significant test results distributed by the organizer. In that results, our system is significantly better.
I mean, those 3 groups. FIB.
Oh, you mean this one? Yeah.
2 groups perform similarly?
I think it's difficult.
What's the meaning of those bars?
I think this is a box plot because the scores of each listener gives are from 1 to 5.
Okay.
So that means it's a discrete value for each for each listener. Then this means this solid line is the how to say the media of the mean, not mean the.
Oh wow, so it's much better than others.
Yeah, and this box is how to say the variance, variance, yeah.
Standard deviation.
Standard deviation, yes. Maybe 0.5 times standard deviation. Oh, how I remember. It should be explained in this way. Half of the training samples are located in this box. Half of the listening samples are in this box.
Okay. So this is the organizer's diagram, right?
Yeah, organized diagram.
Okay.
Yeah.
So if you go to the next.
So what do you mean similarity here? Similarity means what?
Similarity means
naturalness, intelligence.
No,
right?
similar to the original recording.
similar to the original speaker's recording.
Okay, so what does it measure? It's neither naturalness nor intelligibility.
I think there.
So this one tests the adaptation algorithm.
I think it's related with For example,
It's more naturalist.
if a speech sample is very unnatural, it cannot get a high similarity score. But if you have a natural, if the sample is very natural, but it sounds like another person, not the target person.
I see. Okay, so you divide naturalness into 2 categories. One is the absolute naturalness.
Yeah.
You know, without speaker identity. The other one is naturalness with respect to a particular speaker.
Yeah.
Okay. I see.
So here,
Okay, so that's
naturalness wise,
that's Moss. But why do they have the fixed box, right? Normally I said that if it's an error bar, you know, if it's the bar, then you actually will see something more than it doesn't span the whole 1 unit. So yeah, that's the same question that now you were asking.
Yeah.
So the mass score is 3.8, right?
This is the
that's
mean.
your system.
Yeah, that's our system. Yeah.
Then it's supposed to be somewhere 3.8 and then with the error bar.
Yeah, something like that.
So it doesn't look like that. I don't know. So I don't understand what is the box representation here.
You mean this?
Yeah.
That is the median of the distribution.
It's a median distribution.
Yeah, so it must be a value of 1, 2, 4, 3, 4, 5. So that is the median value, not the mean.
Median. Okay.
It's the median.
So it's 3.8. So where's the 3.8 here?
3.8.
Coming from here.
No, we cannot get 3.8 from this figure. Just calculate from other sources.
I see.
This figure just shows the distribution of the scores.
I see. Okay, I see.
And the scores actually are in some discrete.
Discrete. Okay.
There are only.
So just your group and two other groups are doing equally well. The other groups are not as good. That's all we can see.
You mean here?
Yeah, just from.
Yeah, I think the median is almost the same, but there are also some results for the significant analysis. Significance analysis, yeah, we can show that our system is significantly better than this.
Oh, really? Oh, okay. You can see that from here, huh?
We cannot see from
the
here.
The first one and the second one, you can see that.
Yeah, there are some other. There are very detailed results of the.
I see. So is this for Chinese or for English?
It's in English.
For English.
I can show you some samples.
Okay, so your group is doing both English and Chinese, and both are probably the best.
Because every year, in several years, we have more than one language evaluation, but this year we have only the English.
English only. Okay. So does this test have Chinese as well?
You mean the listeners?
Yeah. No, for this year's test.
You mean the
challenge? This year's challenge.
You mean the participants?
Yeah, participants.
I think there is no other institutes from China.
China, I see. Okay.
Okay, this is a new measurement this year. That is for some paragraph test. That means we synthesize some. That means the listeners, what the listener heard is not a sentence by sentence, but a whole paragraph of novel. So they can give some impression scores on these 7 aspects. And the range I remember is from 10 to 60. This is the score of the natural species, and this score of our system is also the best performance in all the 7 aspects compared to other systems. So I can show you some demos of this. We have different types of synthetic sentences. Some are book sentences, some news, and book paragraphs.
Okay, but for this, that's not SUS. Because this
No. Yeah, there are some SUS sentences, but I didn't put the samples here. But because I think that's
so
maybe.
Is only to look for the naturalness.
Yeah, I think these 2 parts are used for the similarity and the naturalness test, and these parts are used for the paragraph test.
Once more the original verdict was sustained. All that little world was drunk with joy. I've liked him ever since he presented this morning. Her research is the second piece by Edinburgh University scientists highlighted recently.
Which one? This is the original one? This
No, all the synthetic speech.
All synthetic speech?
All these samples are synthetic speech from our system.
Oh, okay.
This is a paragraph.
So it was warm and snug within, though bleak and raw without, it was light and bright within, though outside it was as dark and dreary as if the world had been lit with Hartford gas. Alonzo smiled feebly to think how his loving vagaries had made him a maniac in the eyes of the world, and was proceeding to pursue his line of thought further, when a faint, sweet strain, the very ghost of sound, so remote and attenuated it seemed, struck upon his ear.
Okay.
So which one? What's the difference between this one and this one?
No difference, just 2 samples. Just 2 samples. Yeah, sorry, I haven't explained that. I think the text of the book paragraphs are taken from maybe another story of Mark Twain, which is not contained in the training set. Okay, finally, I will give summary of this presentation. In this presentation, I introduced some basic techniques of Hidalgo model-based synthesis. I think the key ideas is that there are 2 models are used. One is the source filter model, used to extract acoustic features and used to reconstruct the speech waveform. And the second is the statistical acoustic model, which describes the distribution of acoustic features for different content information and used to generate acoustic features from this model. This HMM-based speech synthesis method has become more and more popular in recent years, but it's still far from perfect. There are still many points need to be improved. And then I introduced some recent advances of this method, which were conducted in our lab. In order to get better flexibility, we proposed a method of integrating articulatory features into HMM-based speech synthesis. And in order to get better speech quality, we proposed the minimum care divergence-based parameter generation algorithm. For better naturalness, we use the hybrid Hit-Markov model-based unit selection approach.
But quality and naturalness, are they similar?
They are related, but I think the speech quality is more related with the spectral parameters. For example, you can feel the buzziness or almost smooth. And the naturalness is more related by more factors. For example, the prosody, yeah, or some other things.
So quality is a subset of naturalness.
Yeah, it can be. For example, if you judge the naturalness of a sentence, maybe speech quality is one of the factors you need to consider. Okay, that's this end of my talk. Thank you.
Very much. Okay, great. Yeah, so I think we asked all questions already. Okay, thank you.